Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about the average value of a function. So let's say we had a set of elements like this. How would we go about computing the average value for this set? Well, I think the answer to that is pretty easy. We would simply sum up all of the numbers in the set and then divide by the total of numbers in the set. And so we would get that this would be 10 over 4, which can be reduced to 5 over 2 or 2.5, which makes kind of sense. Now let's kind of scale this example of what we're doing here to a function, because that's what we're going to be talking about today. Let's say we had this function right here. How would we find the average value of this function? Well, I think the answer to that would be pretty similar to what we had here. Essentially what we're going to do is we're going to find all of these values all across here, and then we are going to divide by the total of number of values that we have computed, right? So my proposition to you is let's divide this function into n intervals. Once we have divided this function into n intervals, we would basically get n values. So let's say all of these dots, let's say there are n of these dots. All of these dots would represent f at a certain x value, and then those would be our values, and then we would divide by n. So a quick and easy equation to write out would be that we would get f at x1 plus f at x2, and we would do this, we would sum up all of these y values up until xn, so the nth x. And this would give us kind of like the top. We've essentially summed up all of the values, and all that's left to do is divide by the total number of values that we have, which happens to be n. But now let's think about kind of working towards getting rid of this sort of n, and I'll show you why later. If we think about it, n intervals, right? This means that every interval is exactly, I'm going to label this as delta x, it's exactly b minus a over n thick. The reason for that is, again, we've kind of seen this in previous lessons, but if this is b right here, and then this is a right here, if we have split this up into only two intervals, right, well then the thickness of each interval would just be b minus a divided by 2. But if we have n intervals, we kind of need to compute what is the total thickness. So what we do is we take total distance kind of between a and b, and then we want to divide this into n parts or intervals. So therefore the thickness for each interval would be given by this formula right here. And like I mentioned, we want to kind of get rid of n, so what we can do is we can quickly isolate for n, and would be b minus a over delta x. So now we have a formula for n, and we want to sub this in to this n right here. Let's go ahead and do that really quick. There we go. We have subbed this formula right here in for n, and now what I'm going to do is I'm actually going to factor out this right here. I'm going to factor out this b minus a, and I'm going to swing this delta x over to the top. So I'm just going to change the way the function sort of looks, not the way it behaves. So there we go. Again, I have factored out this 1 over b minus a, and I've sort of brought up this delta x to the top. Now if we go on to expand this, we're kind of going to see what we are getting at by substituting this in for n. I have distributed delta x into this bracket, and now we can rewrite this right here as a summation instead of using these like 3 dots. There we go. We have rewritten this chunk as a sigma function, and essentially what we're going to do is we're going to sum up each element, and each element consists of f at x at a certain I, and I ranges from 1 all the way to n, so that's why we have these bounds set on our sigma function, and we want to sum up f at xi times delta x. And again, we've seen this quite often now, but this right here is equivalent to the integral. And now you can kind of see why we have wanted to sub that in for n. We've basically ended up at an integral notation for the average value of a function. So in reality, this is all there is to the average value of a function. It's a simple formula. Kind of showed you how we can come to that. It's not a formal proof, but it kind of just gives you a little bit of direction. If you're ever stuck and you want to kind of figure out how we can derive it, there it is. But yeah, it's just a formula, and essentially you're just going to apply it. So I'm going to throw in a quick example how we can apply it, but it's going to be pretty easy. So here's our example. It asks us to find the average value of the function f of x equals 1 plus x squared on the interval -1 to 2. So we know that the function's average, well, that's going to equal to 1 over b minus a times the integral from a to b of f of x dx. And the question actually gives us everything that we need. So this is just going to be equal to 1 minus b is the endpoint of our interval, so it's 2, minus, and then a is the start point, which is -1. Now we want to plug the same a and b into here, so from -1 to 2, f of x is given to us in the question, so this can be 1 plus x squared dx. And again, you guys have seen this integral plenty of times. I'm sure you know how to do it by now. So I'm going to skip forward and just show the answer. So there it is. There is the average value of our function. It's pretty easy. Again, it's a formula. I just wanted to show you how we can use the integral and kind of apply it to the average value of a function. So that's it for today's video. It's been pretty short. Hopefully you've enjoyed it and learned something. If this video has helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. And yeah, I will catch you guys in another video.